G'day and welcome to topic one video for ACC515, which is just a brief introduction to financial mathematics. So in the previous video tutorial we looked at what is finance, which was concerned with developing analytical tools to assist managers in their financial decision making. And one of the things I said that it was useful for is in deciding what is the value of a future cash flow. So what's the value of a McDonald's franchise? What's the value of any investment? And that, given that we can work out what the future cash flows coming from those investments are, how do we value what they are today? And a key concept that is understanding the time value of money. So how the value of money changes over time. And we change it by compounding and discounting. So what we're trying to do is work out what a future value might be worth today, or what a value today may be worth at some time in the future. And how do we do this? Well, we use financial mathematics. But to give you an idea of how the problem is, let's just imagine for a second that I owed you $1 million, and which is due to be paid a year from now. We're going to assume, and this is not true, but we're going to assume that there's no risk. I will pay it. So how much would you accept if I offered to pay in cash right here, right now? So I don't really want to be left, with that debt hanging over my head. I want certainty. I want to pay it now. This problem happens all the time. So for example, when you see those lotteries that offer to pay you $25 million a year for the next 10 years, or $50,000 a year for the next 10 years, there's various versions of them around. They don't actually pay you that money each 10 years. They come to you and make you an offer about how much they'll pay you in a lump sum today. They don't want the bookwork of having to remember to pay you every 10 years. And if you're the person receiving it, you may not want the risk that something won't change over those 10 years time, or that you might, heaven help us, pass away or something like that, so you won't get the full benefit of it. So future cash flows get turned into present cash flows all the time. So how much would you accept today if to settle my debt of $1 million? So think about it. Again, assume there's no risk attached to the future payment. Just imagine there's some elevator music playing in the background. And I want you to think about what you would accept. Okay, time's up. I didn't give you long. So what if I offered you $800,000? Would you accept? 850? In your hot little hands right now. Okay, so let's settle on $900,000 paid today in settlement of $1 million in 1 year's time. Pretty generous, I would have thought. And that's what our cash flow is going to look like. So present value is today $900,000, and the future value in 1 year's time is $1 million. Seems good. You can have that $900,000 today, this afternoon, in cash. Do with it what you will. So we all sort of understand intuitively that receiving $1 today is worth more than, or is better than, receiving $1 in the future. And the opportunity cost of the dollar in the future is the interest we could have earned on the dollar if received earlier. And that gives you a hint as to how we work this out. So how do financial managers compare projects with different cash flow timings? What would you prefer? A bird in the hand or two in the bush? So $900,000 today, or $1 million in the bush? Or what if it's 10 in the bush? We don't really know. How can you compare something today to something in the future? So when we discount and compound future cash flows, that enables us to compare apples with apples, not apples with oranges. So money in today values is apples, money in the future value is oranges. You can't really compare them. Some people like oranges, some people like apples. But if we're looking at two apples, we can compare the quality of those apples. Much the same as if we convert them both to future values, we can look at two oranges and compare. So, but we can't compare them if they're not in the same time period. So we've got to look at how can we discount the future cash flow back, so we can compare it to present values today, or how can we compound the present value forward so we can compare two present values to future values at the same time. So you can only make comparisons if values you are comparing are in the same period, i.e. today or in 1 year. So it's impossible for you to say, 900,000 is better than $1 million in 1 year's time without doing the comparison, without bringing them into the same time period. So what would you have agreed to in accepting 900,000 today to settle my $1 million debt to you? What would you do with 900,000 once it arrived in your little band? Would you pay off some debt? Would you go on a holiday? Would you invest it? What would you do? And what did you hope to earn? Accept that we're probably not going to be able to spend the whole 900,000. You might have a $900,000 mortgage, and you could pay that off. But with that $900,000 mortgage, mortgage rates at the moment, 5% is an expensive one. So you will save yourself 5% on that debt. But in accepting 900,000, you've actually determined that you expect to earn 11.11% on your $900,000, which is probably more than you're going to get in the stock exchange, certainly more than you're going to get on a retail investment. So you're still happy? Are you glad you took that offer? So I've been able to work out it's 11.11% by doing a really simple financial maths calculation to work out what's that equivalent to interest of. So let's say I'm in business and I can get do an interest borrow at 8, let's say at 8%, which is quite high given the time being. So if I knew that you'd accept 900,000, I'd be crazy, and I wasn't going to have the $1 million to repay it. I'd be crazy not to borrow that $900,000 today, give it to you, and then in 1 year's time at 8%, I'm going to owe 972,000. Presuming my maths okay. Normally it is. What's that? 8 times 12. 96,000. So I'm better off to borrow and then repay it in 1 year's time when my $1 million arrives, and I'll be well in front. Given that 8% is a fair bit lower than 11.11%. That's in essence how we do that calculation. So just be aware that intuitively it's worth more. Money today is worth more, but we should still do the calculation. So getting on to compounding and discounting. Compounding is when we translate $1 today into equivalent future value, and discounting is translating a future $1 into its equivalent present value. So compounding and discounting are the terms that we use for that. Compound interest is interest paid on interest. So it's not simple interest. So it's a situation in which interest is paid on the investment during the first period is added to the principal, and during second period we earn interest on the total amount. Interest can be compounded annually, monthly, weekly, daily. You can actually do continuous compounding. And money invested at compound interest accumulates at an increasing rate each period and shows exponential behaviour. So it's important to understand how compounding works, and it's because of compounding when we're doing financial management problems or financial mathematics problems in financial management, you don't simply divide and multiply. All right, you've always got to work out what the compounding is. So the periodic rate of compound interest is defined as I, and you can find it by the following equation where I equals J over M, and J is what we call the nominal annual rate. So if, let's say, the nominal annual rate is 12% and it's compounding quarterly, all right, the effective annual rate will be higher than 12%. And the total number of compounding periods, n, is given as n equals m times t, where m is the number of times it'll be compounded per year. So if it's monthly, it'll be 12. If it's quarterly, it'll be 4. If it's daily, it'll be 365. And t is the number of time periods or years. So interest paid on investment is added to the principal, then interest in the next period is being earned on the total sum. And these are some of the key terms that we use. So how do we work out what the future value is? A very simple problem. FV equals PV plus interest. So for a single period, that's our formula. The future value at the end of the nth period can be determined using this equation, where we simply put PV times 1 plus I to the power of n. And to make it simple, if we're investing $100 at 10% and our FV is 1 year, we know that 100 times 10% equals 110. If we extend that to 2 years, all right, we're going to have our future value, FV2 equals our future value 1 plus 1 plus I, which is going to equal PV times 1 plus I times 1 plus I, or PV 1 plus I to the 2, and then we can see how the n works to compound. All right. In purely mathematical terms, we would take our first year value. So if we've rolled over our investment, which has grown to 110, we would then be earning 110 at 1 plus I, which will take us to 121. Or if we started at the start, we say FV, future value year 2, equals PV 1 plus I to the 2. So we get $100 plus 1 times 1.1 to the 2, and we get the same answer. So it just shows you how the formula works. And we can do that to the power of n, to the power of 8, to the power of 10, to the power of 100, to the power of 200. We can move that amount and find out a future value for that at that particular rate of interest at any time in the future. And the amount that we work out there is called the future value interest factor, but we pretty much expect you to be able to calculate that on your own, even though they can be obtained from tables or whatever. So you can use a financial calculator. These are the things for the Sharp EL735. There's probably a later model than that now. They're all pretty similar, but if you've got a financial calculator, please learn how to use it. So how do we calculate future value in single sums? So if you put $100 in an account earning 6%, we know that's going to be $106. If we look at the time period, you can see how things, and probably the one I'd like you to look at is the bottommost right hand corner number. So if we invest for 9 years, where n equals 9 and I equals 10%, we can see our amount of money is more than doubled at that rate. So that table just gives you an indication of how quickly compounding changes when you use interest rates and time. So if we're going to look at the same $100 at 6% but over 5 years, so the formula is FV equals PV 1 plus I to the n, where PV is 100, I is 0.06 and n is 5, and there we get our answer of $133.82. So it's quite simple, the mathematics. Just be careful whenever you're using tables. You get slight round off errors. We don't mark you down. So if you used a table there, you would have got an answer of 133.8 rather than the correct answer of 133.82. What about when we have quarterly compounding? How does that impact on it? I'll let you guys do that, but essentially all you do is 1 plus I over m, or j over m, and then n times m. So the I was 6%, so 6 over 4, because we're compounding 4 times, which becomes 1.5%, and then our n is 5, and that's multiplied by n, which is 40, so it becomes, which is 4, so it becomes 20. So our formula becomes 100 times 1.015 to the power of 20, and that will give you your answer. Whoops, went the wrong way. Which is 134.69. So that's calculating future value. Present value is going the other way. That's discounting. So the present value is the current value of a sum of money representing a future payment that is discounted at an appropriate interest rate to reflect the time value of money and other factors. The discount rate is interest rate that converts a future value to the present value. So we manipulate that single sum formula that we had before, which was FV equals PV 1 plus I to the n, and it can be manipulated to be PV equals FVN divided by 1 plus I to the n. There's a couple of other different ways it can be written, and I've got those there. The one I prefer to use is the third one. So present value equals future value n times 1 plus I to the minus n. So rather than having to divide it 1 over, you just put it to the negative n. And putting something to negative n is the same as putting 1 over something. So, for example, to reach a saving target of $3,000 after 2 years at 8%, how much would I need to invest today? So if I've got a target of $3,000, what do I need to put in today? And we can substitute that in. We find out that if I invested $2,560.47 today, at 8% compounded quarterly, I will end up with $3,000 in 2 years' time, which is what I require to have. So if you receive $100 in 1 year from now, what is its PV? If your opportunity cost, now really quickly, you simply do $100 divided by 1.06 to calculate that, and you get the answer of 94.34. And just to give you an idea of how quickly it depreciates, so if we had our $100 and we invested for 9 years at 10%, looking in the bottom right hand corner, that $100 would have that $100 in 9 years time is only worth $42.40 to us today. And what that means is if you said, oh look, I'm going to pay you $100 in 9 years time, or I'll give you $42.40 today, I don't care. They're equal. If I expect to earn 10%, they're both equal to me, and I don't really have an opinion. If you offered me $42, I would take the 9 year times payment. If you offered me $43, I'd accept the $43 today. So I'm ambivalent between $42.40 and $100 in 9 years time if I expect to earn 10%. So there's just solving that one. So in 5 years time at 6%, that's only worth $74.73 to me. Now, just to make sure you understand that if you put that $74.73 in as a present value and calculated its future value, if you invested at 6% for 5 years, the answer would of course be $100. So you end up the same way no matter which way you go. The answers don't change. So once we have something as a single sum, we can move it. We can move that value through time. We can go 100 years forward. We can go 100 years back. And that's just a calculator solution. So for single sum problems, there's only 4 variables: FV, future value; PV, present value; I for interest; and N. Now, in finance textbooks, I is often shown differently. So sometimes you'll see it as J, sometimes it's R. There's no accounting for it. It's just the preferences of different authors. Payment is always zero because it's a single sum problems. We use payment in annuities. Typically you'll be given 3 variables and asked to solve for the 4th. And this makes solving time value problems really quite simple. So calculating rates of return, solving for I. So again, we just use the same formula. So if future value we expect to have 11,933, we've paid in a present value of $5,000. So we want to know what we've earned on that purchase, on that transaction over the 5 years. Yep. That's the calculation, and that's the calculator solution. The mathematical solution is this one. So just using our basic formula, PV equals FV divided by 1 plus I to the n, and we've substituted in our data. We've got to solve for I, and we end up with 1 plus I to the power of 5 equals 2.3866. Now we've got to take the 5th root of 1 plus I, which means we've got to take the 5th root of 2.3866, and taking the 5th root of something is the equivalent of putting it to the power of 1 over 5, or to the power of 0.2, and of course we get the same answer, I equals 0.19. So determining an unknown I, you can use this formula given here. And remember, that's simply a manipulation of the original formula we started off with FV equals PV 1 plus I to the n. So assume that 2 years ago an investment of $10,000 was made. The investment has grown to a sum of $12,668. The interest is compounded quarterly. Has the investment earned at least 12% per annum? So if we substitute in the equation that we've given you up there, we work out that our nominal rate is 3% per quarter, which is a nominal rate of 12% per annum. You might find it simpler to just use the original equation and substitute it in rather than remembering a completely new equation. As a bit of a hint, I've already talked about this just a second, so you might have worked it out. But if we've got the 4th root of 16, now, because we're all mathematical savants, we know that 2 to the power of 4 is 16. 2 to the power of 2 is 4, 2 to the power of 3 is 8, 2 to the power of 4 is 16. So the 4th root of 16 is going to be 2. But this is just to show you how you can work that out. So 16, if we had the 4th root of 16 and we want to work it out, most calculators don't have, the 4th root or the 5th root or the 6th root. So, but what you can do is put something to the power of. So the 4th root of 16 is the equivalent, is equal to putting 16 to the power of 1 over 4. So 16 to the power of 0.25 is 2. So you can try this. For example, we know that 3 to the power of 3 is 27. So if you put 27 to the power of 0.333, which should give you the 3rd root of 27, you'll get the answer of 3. So assume that 2 years ago an investment of 10,000 was made. The investment's grown to 12,668. The interest is compounded quarterly. Has the investment earned at least 12%? Blah, blah, blah. So 12,668 equals 10,000 times 1 plus I to the 8. And then we substitute in. We end up with 1.2668 to the power of 0.125 equals 1 plus I equals 1.03. Solving for n is a little bit more difficult because you use logs. Now, calculators will generally give you 2 different types of log. Doesn't matter which one you use, just so long as you use logs, the same logs for both sides of the equation. Obviously, the calculator solution is pretty quick. You can use this formula here, but I think it's probably easier to just remember the one formula, which again is this future value formula. So we've got a future value of 358.84, a present value of 300. We've got an interest rate of 12% compounded monthly, so 1.01 by the time we divide it by 12, and then n. Remembering we're going to find an answer in months here as well. So 358.84 divided by 300 gives us 1.1961333, and that equals 1.01 to the power of n. So how do we get the n down? So what we find is that the log, if we take the log of both sides, the other side will be then multiplied by n, and then we can now divide both sides by the log of 1.01, and we've isolated the n. So when I've calculated the log, and I can't remember which logs I've used here, but the log of 1.19613 becomes 0.17909 blah blah blah, and the log of 1.01 becomes 0.000995 blah blah blah, and that equals 17.9988 or 18. So that's how you solve that mathematically. You can use spreadsheets for time value of money problems also, so there's a bit of a hint. This is just a quick introduction to single sum problems and how to do them, and I'll do another video on annuities shortly. Thanks very much.